Physics students, welcome to topic 9.5, one of my favorite topics in physics. It's called the Doppler Effect or the Doppler Shift. We've studied this a little bit, maybe referred to it before. We're going to talk about it a little more formally now. We're going to quantify it. It turns out the mathematics can be a little bit difficult, but I'm going to walk you through that. This is important for two reasons. Number one, we hear it all the time. Okay, we hear the Doppler effect with sound and pitch, and you probably can think in your mind of like a siren or a car with a beeping horn going past you. Okay, because light behaves as a wave, we also see the Doppler effect with light, and that affects frequency and color of light. We also see the Doppler shift. It's also relevant with respect to waves from a boat on a lake and so forth, but we're not going to really focus on those cases. We're going to focus on sound and light. Okay. You know that the frequency of sound waves is proportional to the pitch that our ears actually hear, right? So the higher the frequency, the higher the pitch, okay? And let me play this video, and you can think if you've, when was the last time you experienced this? Okay, so what's happening here? Well, the person driving the car is beeping the horn. The horn has a constant frequency, okay? The person driving the car hears the horn at the same frequency the whole time as they're driving down the road. Clearly, from our vantage point here, the pitch starts off high and gets low. It's high as the car is approaching us and low as the car is going away from us, okay? All right? To us, the frequency is changing. Clearly, it's going from a high frequency to a low frequency. But again, the frequency does not really change, okay? This is an apparent change in frequency due to the relative motion between the source of the wave and the observer, okay? All right, so I'm going to define for you what I mean by the Doppler effect. The apparent change in frequency of a wave when there is a relative motion between the source and the observer. It occurs with electromagnetic, sound, and water waves, okay? And what happens, I love this simple little diagram because it's so straightforward and easy to understand. The wave fronts actually get bunched up in front of the moving object, okay? So the wavelength gets lower, so therefore the frequency increases. On the other side, the wavelength gets stretched out because the waves are sort of left behind by the moving car, okay? And as the wavelength goes up, the frequency goes down, okay? So we hear a high pitch here and a low pitch there. It's as simple as that, okay? But I'm going to quantify it for you, and the mathematics can get a little bit complicated, but it's nothing that you guys can't handle, okay? Turns out that our ears are super sensitive, okay? We can hear frequencies between 20 hertz and 20 kilohertz, okay? Below 20 hertz, we call that infrasonic, below, and above 20 kilohertz is called ultrasonic, okay? It's quite amazing that our ears have developed to be so sensitive, okay? So consider again a moving fire truck. This is essentially the same diagram I showed you in the previous slide. If the truck is at rest, the two people on either side hear the same frequency, okay? You see the wavelength is the same distance on either side. As the truck is moving, what happens on the right-hand side is that the wavelength goes down because they get bunched up, so the frequency goes up. So the person on the right will hear a higher pitch. On the other side, lower frequency, greater wavelength, lower pitch, okay? The velocity of the sound in the air is actually important. And the velocity of the sound in the air is, of course, given by v equals f lambda. So again, if the wavelength increases, which is behind the truck, the frequency decreases, which means a lower pitch. If the wavelength goes down, which is in front of the truck, the higher the frequency means a higher pitch, okay? What is moving is very important, okay? So I'm going to give you a couple of cases. Number one, if we have a stationary observer and a moving source, can you guys hear that? Yeah. Notice that the frequency, again, is higher, and this is cool. The frequency is higher as it's approaching this. Let me just explain this a little bit. This thing right here is a microphone. The thing that was moving was the actual source. I'm going to play this again, and you can see, I'm going to show you several different videos of this. You can see the waves, and every time the wave front hits the microphone, you hear a little ticking sound. So you can hear that there are fewer wave fronts hitting the microphone per unit time as the actual source is moving to the right away from the microphone, okay? So that's a stationary observer. In that case, the observer is the microphone and the source is what's moving, okay? As an ambulance would be something like this. Okay, and we've all heard that in real life, right? Okay. All right, case 2. We have a stationary source and a moving observer. It turns out that it sounds the same in terms of a high pitch to a low pitch, but the physics, the mathematical modeling is actually a little bit different, okay? So let's check it out. So here's a stationary source and a moving observer. So higher frequency, lower frequency. Okay, so it's the same general trend as before, and again the ambulance. Okay, I just realized how disturbing it is that there's a floating ear that's moving. Anyway, okay, and these two graphs right here are really interesting, okay? These graphs tell you the frequency against time. So you can see the frequency is high, and then it gets low, okay? Now, something really important, you actually, as an observer, whether you're in the car or not, or on the side of the road, there is actually an instant in time where you are hearing the real source of that or the real frequency of that source, and that is when the line of sight between you and the velocity of the relative velocity is perpendicular. Okay, I'll talk about that a little more later. Okay, so let's get a little deeper into the case of a stationary observer and a moving source. Okay. I'm going to do some math here for you guys, so get ready, okay? I'm going to call stationary observer. Well, I have two observers. I have these people with glasses on. I don't know why. Number 1 and number 2. One is in the direction to the right of where the car is moving. The other is sort of on the other side, okay? You can see the waves get bunched up, the blue waves on the leading side, and they get stretched out, the red waves on the other side, okay? I'm going to call the velocity of the green car u sub s, okay? That's the velocity of the source, okay? V in this case is the speed of sound in the air or through the medium, okay? Okay, so the car starts at the red spot with a v, or with a speed u, okay? For t seconds, producing a sound of frequency f, okay? In a time t, the car produces, obviously, f times t complete waves, right? Think about that, okay? Ahead of the car, the waves are squashed into a shorter distance, and that shorter distance is given by vt minus ut, okay? That's the distance that they're squashed into, okay? Then if we consider the wavelengths, okay? I'm going to call lambda prime, okay, which is the actual wavelength that the woman, that I guess it's a woman over here, is hearing, is going to be Vt minus Ut all over Ft. The T's cancel, and you get V minus Us over F, okay? Now, the speed of these waves is V, so you could also, and this just then becomes algebra, if I want to think about it in terms of the frequency instead of the wavelength, okay? It's going to be f prime is v times f, where f is the original frequency, all over v minus u, okay? Or for waves behind the source, the waves are then stretched into a distance, vt plus ut, okay? So it's a similar mathematics, and you have v plus us, okay? In the IB data booklet, they give you this version. That's the reason why there's a plus or minus is because whether it's coming towards you, whether the source is moving towards the observer or away from it, okay? And f prime is the actual frequency that is heard by the stationary observer at that location. V is the speed of sound in the air. So you see, the mathematics is maybe surprisingly complicated, but I know that you guys understand the actual overall philosophy and the big ideas behind the Doppler shift, okay? Okay, so we have a moving source. We're going to check if the source is not moving, does f prime equal f? Yes, because this whole thing in parentheses is 0. And also notice that lambda does not equal lambda prime. Here's my graph of the frequency against distance, okay? The observer, here's where you hear the true frequency, right? Okay, is right here, okay? And again, here's my floating ear in the ambulance. Higher frequency. Right there is where the big ear is going to hear the real frequency as heard by the ambulance driver, and then we have a lower frequency here, okay? So pretty cool stuff. So we've now quantified mathematically, essentially, this graph, okay? Okay, let's try an example. A person jumps off a high bridge attached to a bungee cord. As they begin to fall, they scream at a frequency of 1,000 hertz. As they reach a maximum velocity of 40 meters per second on the way down and 30 meters on the way up, if the temperature is 20 degrees, gosh, what a lot of information. What's the maximum frequency and the minimum frequency you would hear as a stationary observer on the bridge? So in this case, we have a source, which is the person's mouth screaming, that's moving relative to an observer that's not moving, okay? All right, so F max would occur when the person is coming up towards the bridge, right? Okay, so that they tell you is 30 meters per second on the way up. It's a simple application of this equation, okay? And I get 1,096 hertz. So the pitch increases, the frequency increases when the person's shooting up towards you by 96 hertz, okay? The minimum frequency is when the person's going down, falling away from you, okay? And that was given as 40 meters per second as the velocity, so that's 896 hertz. How cool is that? I love it, super cool. Okay, now the moving observer and a stationary source, okay? All right, this is maybe slightly more complicated, okay? We have car 1 approaching the source and car 2 going away from the source. I'm saying that car 1 hears F1 prime and car 2 hears F2 prime. All the variables are the same except for instead of u sub s, I have u sub 0, which is the speed of the observer, okay? All right, again, v is the speed of sound. Observer in car travels with a speed u0, u0. The change in f is due to the fact that the relative velocity changes. So the person here would hear a higher pitch. The person here would hear a lower pitch, right? Okay. Now the relative speed of the sound coming to car 1 is v plus u0, right? Because you're adding the velocities together. So f1 prime is v plus u0 over lambda. But lambda and v don't change, so we have this new expression for v1 prime. You're going to want to pause this frame and think about it. You should be working this out on a sheet of paper and doing the algebra yourself. Don't just listen to me do it, okay? All right. Now, for car 2, receding from the source, we have a different situation where the algebra is similar, but we have a minus sign up top. And in the IB data booklet, this is what they give you, okay? F prime, which is the frequency of the sound as heard from a moving observer, is the original frequency times the quantity, the speed of the sound plus the speed of the plus or minus the speed of the observer divided by the speed of sound in the air, okay? Let's do a quick example. Calculate the frequency of sound you would hear as you drive 20 meters per second towards a sound source emitting a sound of frequency 300 hertz and air at 25 degrees Celsius. By the way, the temperature is important because that allows us to determine 340, 343 meters per second. That part is actually not as important, but you want to note that, okay? In this case, you have a moving observer at a stationary source. I got that F prime was 317 hertz, which means it's a higher pitch because it's greater than 300 hertz. Next one, a car traveling at 30 meters per second emits sound at a frequency of 500 hertz. Calculate the frequency of sound measured by an observer in front of and behind the car. Again, very straightforward situation. In front of, it's going to be greater than 500 hertz. I got 547 hertz. And behind, it's going to be less, 460 hertz. Okay? All right, so higher pitch, lower pitch. Cool. Now, I want to talk about light frequency and the Doppler effect for light, okay? All right. You guys know about the electromagnetic spectrum. You know that light is a very small sort of band in the overall electromagnetic spectrum. You know that the speed of light is approximately 3 times 10 to the 8 meters per second. And by the wave equation, this equals F lambda, okay? Lower frequency of light gives us reds and oranges, and higher frequencies give us blues and purples, okay? Blues and purples have more energy. Those waves have more energy in them than reds and oranges because they have a higher frequency. Light undergoes a Doppler shift also, but the equation is not the same as for sound. In fact, this is a case where light is much simpler than sound. C does not change when the source and the observer are moving relative to one another. So the reason why this equation is different and simpler is really because of relativity, which I'm not going to get into right now, okay? But we're going to use the following equation to approximate the Doppler shift for light. You see, it's much easier. So delta F is the change in shift over the original frequency. Well, that's going to be the change in shift. The shift in frequency over the original frequency equals the change in the wavelength over the wavelength, which is approximately equal to the ratio of V over C, where V is the speed of the source or the observer. So there's no differentiation now between stationary observer, moving source, moving observer, stationary source, etc. Okay? All right, and the relative velocities, we need to make sure that they're much, much less than c. When we get close to c or any significant fraction of c, then relativity takes over and it becomes a lot more complex. So this is all that you need to know is this very simple equation, and of course it's given to you in your data booklet. Okay, again, it doesn't matter whether the source or the observer is moving. Let's try this example. The star emits light of wavelength 650 nanometers, but the light received at the Earth has a wavelength of 690 nanometers. How fast is the star moving relative to the Earth, and in what direction? Well, clearly, because it's the wavelength is going up, right? The frequency is going down. So in that case, wouldn't the star be moving away? Okay, and a very simple, I've actually used the 5-step problem solving method to solve this problem. I got that the star is moving 1.8 times 10 to the 7 meters per second, okay? And it has to be moving away again, right? Because the wavelength is actually greater, which means the frequency is less, okay? Okay, how about this one? A police speed trap uses a beam with a wavelength of 904 nanometers. What frequency will be received by a car traveling towards the trap at 150 kilometers per hour, okay? Well, it would be a higher frequency anyway, right? Okay, so let's work it out. First of all, you have to convert 150 kilometers per hour to meters per second. I got about 42. Wave equation gives us a frequency of 330 times 10 to the 14 hertz. This is the frequency of that light. Of course, they gave us the wavelength, not making it super easy. The change in frequency, I got 4.61 times 10 to the 7th. So therefore, the change in delta F is inconsequential compared to F, right? So that's that. Hold on, when I say inconsequential, I'm talking 7 orders of magnitude less, right? So, I mean, what are you gonna do? Add this to this? You're gonna get no difference in your digits, essentially. That's what I mean by that, okay? All right, I wanna talk about something really cool, the redshift of the universe. We'll talk about this later, but it turns out that astronomers use the Doppler effect to calculate velocities of distant stars and galaxies. Now, astronomers know the chemical makeup of stars and hence their true color. And if we compare the line spectra of light from a star with what it should be, the Doppler shift of the star's light can be measured. Then the speed of the star can be calculated, okay? So stars moving towards the Earth show a blue shift. Stars moving away from the Earth show a red shift. So again, the blue shift means the frequency goes up. The red shift means the frequency goes down, okay? It turns out that all distant galaxies, when you look anywhere in the universe in the night sky, everything is moving away from us. And by measuring their redshifts, their speeds can be estimated. Further galaxies have higher speeds. The most distant ones are moving away from us at the speed of light. And this has to do with a lot of astrophysics, which we'll talk about later. This is one of my favorite topics in the universe, okay? Now, I want to talk a little bit about the Big Bang model. Turns out the Big Bang model is a direct extension of this theory, right? It's believed that the universe expanded from an extremely dense and hot state and continues to expand today. Expanded into what? Well, we don't really know. No one really knows that. But expanding implies that something is getting bigger, expanding into something else, okay? But in this case, expanding means that the galaxies are moving apart from each other. Okay, it's not because they have different speeds, it's because the actual space between them, so space-time, is actually expanding. It's like an expanding canvas. If you paint on a canvas and then you stretch that canvas, the things you painted on the canvas will physically get farther apart, but it's not because they're moving, it's because the actual fabric of what it's on is actually moving. It's very much like the reality of the universe, okay? You can think about it as springs on a road, okay? And the cars upon it as galaxies, right? If you stretch the spring, the cars move farther apart, and the cars see each other receding or approaching one another, right? Okay? The space between the cars increases, but is consistent between adjacent cars. They're not increasing because they're moving. In fact, they're not even moving relative to the spring, okay? This is pretty heavy stuff. Try this example. A spectral line from galaxy A of wavelength 434 is redshifted. Calculate the recession speed, meaning calculate how far it's moving away from us. By the simple application of the Doppler shift for light, I got 3.17 times 10 to the 7, okay? The same line shifted, okay? you get a 3.25 times 10 to the 7. Galaxy B is further away because its recession velocity is greater. Okay, and this has to do with something called Hubble's constant and Hubble's equation, which we'll deal with later. Okay, some other applications of the Doppler effect to round out this now long video, which is now over 20 minutes. Sorry for that. Okay, besides determining recession speeds of distant celestial bodies and speeding cars, we can do things like determine the speed of rotation of the sun. And what we do is we take photographs of the opposite edges of the sun. Okay, each contains what we call absorption lines due to elements such as iron, which are vaporized in the atmosphere of the sun. Okay, when the photographs are put together, the lines and the spectral lines in the two photographs are displaced. Okay, so this light coming from this side of the sun, okay, has a higher frequency than light on this side of the sun that's going away. And we can figure out that the rotational speed of the sun is about 2 kilometers per second. How awesome is that? Okay, in medicine, we can measure the speed of blood flow through arteries, and we can determine whether blood is moving away or towards a sensor. And so like in this particular video, I don't know which is which. Usually moving away is a warm color and moving towards is a cool color. I don't know. Okay. In meteorology, how do meteorologists know when there's a thunderstorm warning, right? Well, what they do is they look at the wind fields inside of a thunderstorm, and they can tell due to the Doppler shift. Here's a radar signature that indicates a tornado. If you have a very strong delineation between winds moving away and winds moving towards the sensor, which is called the next rad unit, usually that means that the air is rotating, right? Because part of it's moving away very quickly and part of it's moving towards you very quickly. And that usually means that there's a funnel cloud or a tornado. So really practical uses for the Doppler effect.